Okay. So, today we discuss an important topic, that is in fact we start this topic, sequences of random variables. You see, we started with first a single random variable, right, and we considered a function of a single random variable. Then we generalize it to, two random variables. Okay. So, you can even say that it is a sequence just of two elements, two random variables, two element sequence, and we consider a function of two random variables, then two functions of two random variables and all that, right. That whole treatment will now be generalized, where we will be considering a vector, say x as x1 dot 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 x n. This x will be called a random vector if each element x1 to xn is a random variable. That is, x will be called a random vector or say sequence if each x I is a random variable. Okay. So, you see earlier we considered two random variables. So, we had a vector of two elements x 1 and x 2, we call it x y, this is defined notation, but now it is more general, n such random variables, right. So, from a hindsight you can see that if you talk of the joint density or joint probability distribution of x, it will be basically a function of n variables, right, x 1 to x n. Okay. So, we can define joint probability distribution actually I should write like f x, where x say takes values x 1, the specific values x 2 dot 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 x n, okay. And this capital X actually is the vector consisting of the variables small x 1 dot 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 small x n. Here capital X 1 is a particular value for small x 1 is the variable, capital X 2 is a particular value for the variable small x 2 and likewise. What does this mean? It means the probability of this event, that x 1 is less than equal to capital X 1, x 2 less than equal to capital X 2 dot 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 x n less than equal to capital X n. This should occur jointly. There are n joint events, that is, one is small x 1 less than equal to capital X 1 and there is small x 2 less than equal to capital X 2, so on and so forth. Okay. This should occur jointly, simultaneously, that is why it is called joint distribution, right. Okay. This is denoted by f x x 1 up to x n. Sometimes when I do not need, I may skip this subscript x and directly put x 1 to x n. I think you can easily understand, okay. Sometimes, but when there is confusion, when suppose I am dealing with two or more than two such distribution functions, then to differentiate between the functions I may put the subscript. Okay. Now, this is for the joint probability distribution. By the same token, you can then define, and you can easily see that this is now a function of n variables, okay, x 1 to x n. By the same way, I can next define the joint probability density function. Joint probability density. This simply you know that we have to differentiate, the joint probability distribution function. So, we define like this p x x 1 up to x n is nothing but del n n times. Okay. I am skipping the subscript here, x 1 dot 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 x n with respect to del x 1 del x 2 dot 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 del x n. This is the joint probability density. What does it mean actually? It means that if you now consider an n dimensional space whose x's are x 1, x 2 up to x n, and there if you take an infinitesimally volume, I mean mass, okay, infinitesimal zone region, okay, whose volume is say dx 1, dx 2 up to dx n, that is along x 1 axis, that is suppose in an n dimensional space you are located at a point up to x n. At this point you are considering an infinitely small or infinitesimal small, I mean region or cell, okay, whose sides are, we call it actually hypercube. Actually in real life cube means it has got only 3 sides, okay, but in an n dimensional space I will call it n dimensional hypercube, whose sides are dx 1, dx 2 up to dx n. So, volume is this. So, basically it defines an area where x goes the variable x 1 goes from capital X 1 to capital X 1 plus dx 1, okay. Capital X 2 goes for, that is this zone, this for variable x 1, then for variable x 2 again this is the range, dot dot dot. Okay. So, that means at this point capital X 1 to capital X n, at that point I am considering a small, okay, cell or small region, okay, in fact it is hypercube I would say, whose sides are of length dx 1, dx 2, dx 1 along the axis x 1, this variable small x 1, dx 2 along the axis small x 2, and so on and so forth. So, I basically cover a volume of value dx 1 dx 2 times dx n. Okay. Then the probability that the random variable x 1, x 2 up to x n, they lie, these variables lie within that hypercube located at this point capital X 1 to capital X n, okay, and of this volume, that is small x 1 lying within this range, small x 2 lying within this range, small x n lying within this range simultaneously. I repeat again, this means that I am looking for probability of these elements x 1 to x n lying within a small hypercube located where? Located at the point capital X 1 to x n, okay, in this manner, that is starts at x 1 along the smaller x 1 axis goes up to capital X 1 plus dx 1. So, side is, it covers a side of length dx 1. Then along the small x 2 axis it starts at x 2 and goes up to x 2 plus dx 2. So, covers a side of distance dx 2 and likewise. Okay. So, at this point capital X 1 to capital X n, a small hypercube is formed, infinitely small hypercube is formed, whose volume is this dx 1 dx 2 dot 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 dx n. The probability of these variables lying within that hypercube together will be given by nothing but, just a minute, that will be given by, I am dropping the subscript this times dx 1 dx 2 dot 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 dx n. Okay. This actually follows from this formula, that basically this is nothing but the derivative partial derivative of distribution function. Okay. So, if you multiply this probability density with dx1, dx2 up to dxn, that gives nothing but the probability of the variables x1 to xn lying within the hypercube located at capital X1 to capital Xn of sides dx1, dx2 up to dxn. Okay. This means that if I consider a region D, okay, a region, arbitrary region in the n dimensional space then probability of this vector x falling within D, that region is nothing but integral, actually it will be n dimensional integral. I will call it over D P x dx. X is a vector, you can say x 1 up to, if you want you can write it like this. Okay. So, you can see that it is nothing but just generalization of our previous concepts. Okay. It is generalization of our previous concepts from 2 variables to the general case of n variables. Okay. Certain more things also you can see, some other things. For instance, if you consider the distribution function f suppose here some of the values I put as infinity. For example, suppose I have got x 1 infinity x 3, then my claim is this will be nothing but the joint distribution for just x 1 x 3. Why? After all, what is this? This is nothing but probability of x 1 like less than this, x 2 less than equal to infinity, x 3 less than equal to x 3. Now, x 2 less than equal to infinity means all possible values of x 2 are covered, right, which effectively means that I am basically looking at the probability just of this event. Okay. So, I am not selecting a particular choice of x 2 because all possible x 2s are covered. X 1 should be less than equal to capital X 2 x 1, but all cases of x 1 will be considered for which x 2 can take value from minus infinity to infinity. Okay. So, this is nothing but your this f, I guess you understand this. I repeat again in case there is a confusion. X 1 less than equal to capital X 2, capital X 1, X 2 less than equal to infinity. I am considering the joint events and X 3 less than equal to capital X 3. This is equivalent to this joint event x 1 less than equal to capital X 1, x 3 less than equal to capital X 3. Okay, because this will, for this I have to consider all possible cases, okay, for which x 2 can take some finite value, some other value, some other value up to infinity, up to minus infinity. So, there the whole range of x 2 is absorbed in this joint event. Okay. So, these two joint events are equivalent, but in this case I am getting the probability distribution for just x 2 x 1 to x 3, which means in general if this probability distribution function of n random variables, okay, if I put infinity for some, then what I get is nothing but the joint probability distribution of the rest of the variables. this is most important, right, rest of the variables. Okay. And then you differentiate it with respect to those variables, those remaining variables, you get the corresponding joint probability density. That is just by the normal definition. So, this is one aspect. Similarly, suppose this probability density function, say an example, take an example, say x 1, x 2, x 3, x 4. Suppose I integrate it with respect to say 1 or 2 variables, not all of them, because if I integrate with respect to all of them, I get 1 of course, because total probability is 1. But suppose I integrate it with respect to say 2 variables, say dx 2, dx 4, minus infinity to infinity, and this is my x vector, where x vector is x 1, x 2 up to x 4. I put a subscript here purposely. What does it mean? You can easily see, you can write this as conditional probability of given some x 3, x 4 times p x 3, x 4 dx 2, dx 4. Sorry, there will be some change here. Which is x 1, x 3. Okay. Now, p x 1, x 3 go outside, because integration is with respect to x 2 and x 4, and if you integrate this part with respect to x 2, x 4 over minus infinity infinity, obviously that will be 1, because subject to this giving condition that x 1 and x 3 are given. Probability of x 2 falling within minus infinity infinity and x 4 falling within minus infinity infinity, that has to be 1, because it covers all possible values. So, you get nothing but p x 1 x 3. That means, if the probability density function of all these random variables is integrated with respect to some of the random variables, then what we get is the joint probability density function for the rest of the variables. Okay. Then you remember when we considered 2 random variables, then we move to function of random variables, and we consider 2 functions of 2 random variables, right. Here what we are given is this x as we consider some functions y 1, y k, our purpose will be to find out the joint statistics, that is joint distribution or joint density, I would say. I mean, both are equivalent, you can obtain one from the other. Joint density say of this random variables y 1 to y k given the joint density or distribution of the random variables x 1 to x n. We have already tackled this problem when n was 2, that is for the case of 2 random variables, we have already tackled this case. That time we took 2 functions g 1 and g 2, okay. But now it is general case, we have k functions. Okay. Obviously, there are 3 choices possible, k can be less than n, k can be equal to n, and k can be greater than n. But we will finally consider only k equal to n case, because the other 2 cases can be easily handled, okay, if we know the result for k equal to n. let us first see how that is possible, and then we will come to k equal to n case and find out the expression for the joint density of the random variables y 1 to y k. First, if k is less than n, then we consider y 1, y 2 up to y k, and then to make the total number of such variables equal to n, I simply add x k plus 1, x k plus 2 dot 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 x n. That is, from this random vector I take out the last n minus k entries. Okay. Now, y 1 is g 1 x, y 2 is g 2 x, y k is g k x, and x k plus 1 also you can say it is a function of x, where given x you only pick up one particular element, that is x k plus 1. X k plus 2 is also a function of x after all, given the entire vector x you just pick out one particular element, that is x k plus 2, and same for x n. Okay. So, then the length becomes n. Okay. We already know the joint density of x this random vector x. Okay. Then for this case, okay, the length becomes the length of this modified random vector, if you call it k prime is equal to n. Okay. And we have already told that for the case where the total number of random variables or total number of function is same as the total number of random variables x, that is n, we will consider that case soon. That theory can be applied here. What I mean is that we have already made this statement that we will state the result for the joint density of the random variables y 1 to y k for the case where k equal to n. Now, that result should be applicable to this modified random vector. Okay. So, when k is less than n, we simply can append some elements from the vector x to make it length n, okay, and then apply the theory which we are going to discuss soon to find the joint density of this entire stuff. Okay. That should not be difficult. Okay. If we look at that theory, we will come back to this later as an application of that theory, when total number of random variable is same as total number of these functions g 1 to g k, that is k, is same as the total number of random variables x 1 to x n, that is n. But when k greater than n, then some problem comes. Here you can see one thing, we consider y 1, y 2 up to y n. So, the length is up to this is same as the total number of random variables x, that is x 1 to x n. Okay. So, that functions y 1 after all is a function g 1 x, y 2 is a function which is g 2 x. So, the total number of functions, okay, up to this is same as the total number of random variables, that is n, but k is greater than n. So, we have got k minus n extra functions. How about that? Because I have to actually find out the joint density of those k functions y 1 to y k, but I have only considered a part of it y 1 to y n. Okay. How about the rest? Now, if you say consider for that matter y n plus 1, which is nothing but say g n plus 1 x. Now, my statement is that most often you can express this x in terms of, that is the vector x, that is elements of x, x 1 to x n, in terms of y 1 to y n. How? That is, we know that y 1 is g 1 x, y 2 is g 2 x, Okay. For example, suppose these are all linear functions, some linear combinations of the elements of x. Suppose y 1 is twice x 1 plus thrice x 2 plus dot 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 plus say 10 x n. Similarly, another, so that leads to a linear equation. Similarly, suppose you get another linear equation here, another here. So, you can solve them and get a solution for y in terms of x. Okay. In the general case, you can get more than one solutions, that is fine, but what it means is this: you can replace x by this y's, either one possible y or several possible y's. Given random variable x 1 to x n, you can replace them by y 1 to y n, right, which means y n plus 1, y n plus 2 up to y k. These extra functions can be expressed in terms of y 1 to y n. Then my claim is joint density of y 1, y 2, y n up to y k can be expressed just by the joint density of y 1 to y n. So, if I find out the joint density of y 1 to y n, that is enough for me. With that, I can find out the joint density of y 1 to y k. Now, how to explain that, I just consider an example. Forget all this for the time being. Suppose x is a random variable and you got this probability density function, say p x, and you define another variable y as 2 x. Now, you have to find out, and now you form a vector, say z as x y. You have to find out p z. My claim is, since y is expressible in terms of x, to find out the joint density of x y, this vector, it is enough if we know the joint density, the probability density of x. P z can be easily written in terms of that. This is not very difficult. What it means is this: suppose x and y is a plane, and this is the line y equal to 2 x. We start with probability distribution for that matter, because that is easier to explain. And suppose you consider any point here, some x and corresponding y. In this case, what is the probability? Suppose you call it capital X, capital Y, this point. So, what is the joint distribution? P x y. That means, what is the probability that small x is less than equal to capital X and small y is less than equal to capital Y? Remember that for any given x, y lies precisely on this line, nowhere else. So, if you are at this point now, capital X, the probability that small y lies below this point is 0. If you go little left, the probability that small y lies again below this height, again 0, because if you are at this x, corresponding y is here on this line. If you are at this x, corresponding y is here, but if you are looking for small y taking value less than this height, so obviously this point is not on this line, so probability is 0. But if you go up to here, call it say x prime, then there is no problem. I mean, x prime or to the left of it, there is no problem, because there is a probability. What is the probability of say x less than equal to x prime, y less than equal to y prime? What will that be? For instance, suppose you are here. Probability that small x is less than equal to this and small y is less than equal to this, what will that be? Obviously, that will not be 0, because if small x is here, y will be here. So, that is less than this. Okay. But then what is the probability then? It is simply the probability distribution of x up to this point. This is because y is purely determined by x. If small x is up to this point, y has to be here. Okay. So, the joint density actually turns out to be just the probability, the joint distribution turns out to be the probability distribution, simple probability distribution of x. I repeat again, suppose you are now here x double prime, okay, or maybe you call this as y prime, forget this. Call it y prime. Suppose your x prime is here and this is y prime. So, now the probability of x taking values less than equal to x prime and y taking value less than equal to capital, say the probability of x here, x taking value x prime and y less than equal to y prime, that is not 0. If you go backward, same phenomenon occurs. That is because for any choice of your x, be it x prime, the corresponding y is here, that is below this height. So, probability is not 0. And then what is the probability of then x lying, I mean what is the probability of x lying to the less of say x prime and y lying to the lying x lying x as less than equal to x prime and y less than equal to y prime, what is the probability? It is simply the probability of x less than equal to x prime, because if that is satisfied, this is also satisfied, because y equal to 2 x. Okay. So, if small x is less than equal to x prime, y has to be less than equal to capital Y prime, because y will be on this line and that is below this height. So, that is automatically satisfied. So, this is enough to have only this. If this is satisfied, this is always satisfied. So, basically this is the event, or these two events are same. I mean this is the event, right. This two, it is not that these two events are same, but this is the event. If this is satisfied, that is automatically satisfied. So, the joint probability is nothing but joint probability of these two events occurring together is simply the probability of this event alone. Okay. Which means, for such cases where one variable is expressible in terms of the other, the joint density of the vector is obtainable simply from the joint distribution of the original vector is obtainable simply from the original probability distribution, and then by the same logic then it applies, I mean and by extension the same logic applies to the probability density functions also. So, this explains why for the case k greater than n, we can just happily take up to y 1 to y n, okay, and find out the probability density of this, because as I told you y n plus 1 to y k, each of them can be expressed in in terms of this. How? Because each of them y 1 is g 1 x, y 2 is g 2 x, y n is g n x. So, if you solve them, then all the elements of the x vector x 1 to x n, they can be expressed in terms of these variables, and by that process y n plus 1 can be written in terms of these variables, y n plus 2 also can be written in terms of these variables y 1 to y n, and like that. Okay. And as I told you, if y n plus 1 is expressible in terms of these variables, okay, or y up to y k, so y k also is expressible in terms of these variables, then the overall joint distribution can be written down just in terms of the joint distribution of y 1 up to y n. Okay. So, this means we can simply take k is equal to n. So, if there are n random variables, we take n functions y 1 to y n. Okay. I repeat, x 1 to x n, there are n random variables and we take these functions, I mean y 1 as g 1 x, y 2 g 2 x up to y n g n x. Okay. In this case, what is the joint density of y1 to yn. That is, what is, you can now put a subscript say y, some values are given. So, joint density at these values, capital Y1 for small y1, capital Y2 for small y2, these are specific values, and small y1 is the variable, small y2 is the variable, and like that. Okay. What is that? We have to find out. For that, first we solve. We solve these equations. First, this we solve. By solving, each component of the vector x, that is x1 up to xn, will be written in terms of y1 to yn, as I told before. Now, possibilities. First possibility, no solution. Suppose no solution exists, then the theory says that this should be 0. It is 0. Then suppose only one solution. The solution is okay. In this case, is by the theory you replace, put the solutions here. So, capital X1 for small x1, capital X2 for small x2 up to capital Xn for small xn. Remember, each of the variables capital X, each of these elements capital X1 to capital Xn, they are basically, I mean expressed, they are basically obtained in terms of y1 to yn. So, this is becomes actually a function of y1 to yn. This is divided by determinant of a matrix. Okay. The matrix is called Jacobian. Again, it is evaluated at this. What is Jacobian? These partial derivatives, but they are evaluated at the solution point. They are not general expressions. Del x 1, del g 2, del g 1 by del x 2 dot dot del g n up to del g n Okay. So, these partial derivatives are evaluated at x 1 equal to capital X 1, small x 2 equal to capital X 2 and dot 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 small x n equal to capital X n. Then this matrix you compute the determinant, okay, and ratio of this will be the probability density. Okay. As I told you, each of these capital X 1 to capital X n, they are actually functions of now, or they are already expressed already by our solution in terms of y1 to yn. So, right hand side actually becomes a function of y1 to yn. And if you have more than one solution, then you will have such terms just added. Okay. Suppose there is one solution x 1 up to x n, there is another solution x 1 prime up to x n prime and call it capital X prime. Okay. In that case, the total probability density will be this plus again p x within bracket x 1 prime dot 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 x n prime divided by the Jacobian, determinant of Jacobian evaluated at x 1 prime to x n prime, and so on and so forth. Okay. That is the theory. The random variables or V's these are random variables, they are called independent. It is just extension of the concept of statistical independence. Earlier we have independence of 2 random variables to the case of n random variables, okay, nothing else. So, they are called statistically independent if you consider the joint event, if the events are independent events. Meaning the probability, the joint probability of these events together, basically the joint probability, which is nothing but the distribution, will be nothing but probability of x 1 less than equal to capital X 1 multiplied by probability of x 2 less than equal to capital X 2 dot 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 dot, that is and as a result, if you have to find out the joint density, then you, as by your theory you have to differentiate this with respect to x 1 up to x n, but if they are statistically independent, the distribution is a product of the individual distributions. So, if you now differentiate the right hand side with respect to x 1, x 2 and x n, then obviously the density becomes what? When you differentiate this with respect to x 1, only this guy is a function of x 1. So, it gets differentiated with respect to x 1, which gives rise to the density, probability density of x 1. Similarly, probability density of x 2, so on and so forth. So, it becomes x 1 just consider an example as to how to apply the theory. Suppose x 1, x 2 dot 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 x n are independent. And you form y 1 as x 1, y 2 x 1 plus x 2, y 3 x 1 plus x 2 plus x 3 dot 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 up to y n up to x n. So, so essentially we have got some linear functions here, y1, y2 up to yn, they are all functions of x1 up to xn, but there are some linear functions of the specific type. Okay. Now, we are given the fact that x1 to xn they are independent and we know their joint density because we know the individual densities. This is given. We have to find out the joint density of y1 to yn by the previous theory. Now, first to do that, we fix up that is we have to find out P y capital Y1 some specific value capital Y2 dot 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 say Yn. Okay. We have to find out, that is we have to find out the probability joint probability density of y at a specific value say capital Y1 up to capital Yn. Okay. And this will be chosen arbitrarily. So, you get the overall function. So, as per our theory, we first solve for x1 to xn given this y1 to yn. Okay. So, you can easily see the solution that x1 is nothing but from this first equation y1 itself, x2 is nothing but y2 minus x1 and x1 is y1. So, y2 minus y1, x3 is nothing but you can easily see y3, if you put y3 here, what is x3? y3 minus x1 minus x2, okay, which is y, which means y3 minus y2, so on and so forth. So, actually in general xk is nothing but yk minus yk minus 1 this way. Okay. So, and the solution is unique. So, it is not the solution does not exist, solution exists, but only one solution, no other solution, probably it is a linear equation. Okay. This is number 1. And how about the Jacobian? To form the Jacobian, first del y1 with respect to del x1 that is 1, because del x1 with del x1 there is 1, and del y1 with respect to del y2, del y1 by del x2 that is 0 because it is not present here, same for other entries. Then del y2 del x1 there is 1, del y2 del x2 again 1, then zeros, then 1 1 1 zeros, 1 1 1 dot 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 1. You can easily know, you can easily see determinant of this matrix is 1, because 1 times whatever be the square matrix, then 0 times the rest, they all go, again apply the same thing here, finally 1 into 1 into 1 into 1 1. So, Jacobian has a determinant equal to 1. So, now the thing is very simple. You can easily see will be nothing but p x at this choice x1 up to x n divided by the determinant that is 1, and we are given the fact that the random variables x1 up to x n they are independent. Okay. So, this joint density is nothing but the product of the individual densities. So, p x1 okay, and capital X1 is y1, p x2 which is y2 minus y1 dot 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 p x n y n minus y n minus 1. Okay. So, you can easily see that the concepts involved here, they are nothing new. They are simple generalizations of the concepts that were valid or that were introduced rather in the case of two random variables. Okay. That is why I am not giving any proof and all that, you can argue about this on your own. So, I stop here today. In the next class, I consider this issue further and go into things like mean, covariance, correlation. In fact, we will have a correlation matrix now, covariance matrix and things. Okay. Again, the characteristic function issue as relevant here, and that takes us to a very important theorem called central limit theorem. Okay. So, that is all for today. Thank you very much. Okay. So, we have been discussing this issue of random sequences, that is just for a recap. We initially started with just one random variable and function of one random variable, then two random variables, then one function involving two random variables and two functions involving two random variables. Here we tried to generalize that to a set of n random variables which are ordered as a sequence x 1, x 2 up to x n, and we first considered one function of such n random variables and then n functions of such n random variables, right. So, there are several issues which we did not discuss last time. They are all just analogous to those issues which we considered in the case of two random variables, say. Okay. So, we will just continue from where we left last time. Okay. But just one remark, we have so long used real valued random variables, okay. But random variables could be complex valued also. So, suppose we have got this suppose z 1 is x 1 plus j y 1 dot 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 up to say z n x n plus j y n. So, z 1 to z n, we have got a set of n complex random variables, right. But remember, each of these z 1 to z n, they have got two components, one is the real component and another is the imaginary component x 1, y 1, and now x 1 also is a random variable, y 1 also is a random variable. Similarly, x 2 is a random variable, y 2 is a random variable. So, a set of n complex random variable equivalently means a set of twice n real valued random variables, which means probability density of z n is same as actually a probability function, probability density function of two n variables x 1, y 1, x 2, y 2 dot 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 x n, y n. Okay. Further, if z 1 dot 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 z n, they are independent, then it means that p x 1 y 1 dot 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 x n y n, that will be like this, which stands for the probability density for z 1, because z 1 has the two random variables, real valued random variables x 1 and y 1 in it, then p x 2 y 2 dot 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 p x n y n. Okay. Then again, suppose we have got a single function g x, x is a vector. Basically, x means actually is a function of n random variables x 1, x 2 dot 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 x n. Okay. Now, by extending our previous argument, we can then say that expected value of g x is nothing but times the corresponding probability density function dx1 dot up to dxn. Okay. Obviously, if instead of this real variables x1, x2 up to xn, we had a set of complex n number of complex valued random variables z1, z2 up to zn, then instead of having a n-fold multiple integral, we would have had a twice n-fold multiple integral, okay, and the probability density function would have been, I mean this is g z1 up to zn, and probability density function as before would have been p of x1, y1, x2, y2 dot 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 xn, yn, and this is the same. Then A will be called a Hermitian matrix. That means firstly the diagonal elements A11 must be A1 star, which means it must be a real valued element. So, the diagonal similarly for A22, similarly for A33. So, for a Hermitian matrix, diagonal entries are real and other entries are conjugate symmetric of each other, like 2/1/8 element of AH, that is second row first column. This is nothing but 1/2 element of this 2/1/8 of AH is same as 1/2 star of A. So, 2/1/8 element is this and 1/2 element of A is this. If you put a star here, you get back this element. That means AH, this matrix, its ijth element is nothing but A matrix, its jith element star. This is the Hermitian transposition. Okay. Now, if A and AH are same, that means A21 and this, that is we should have A21 is equal to A21 should be just the conjugate of this A12 star. Okay. A31 should be A13 star, because this and these are to be same, and likewise. So, the transposition, the Hermitian matrix ijth element, that means I think I continue from here in the next class, because some more properties are to be discussed. Okay. Because this Hermitian matrices, they give rise to what is called the correlation and covariance matrices. So, that is all for today. We continue from here in the next class, because time is up. Thank you very much.